Okay, so let's talk about this question over here. It says that which of the following is an example of disproportionation reaction, right? Now, this is kind of a question which class 11th or 12th class student can also answer it. And it's basically IIT JEE level question. Okay, that's what I can say. It was pretty simple, very easy question. In a disproportionation reaction, what happens that a single entity undergoes, like a same entity undergoes oxidation and reduction both. Okay, so that's the basic way how we understand disproportionation reaction. Now if you look upon the options over here, if you see, so the oxidation state of oxygen is changing. Here the oxygen is in like it's in -1 oxidation state, whereas here it is in -2 oxidation state. So the reduction of your oxygen is happening, and like the sulfur is undergoing oxidation over here. So there are two different species which are undergoing oxidation and reduction. Okay, so it's a redox reaction, but oxygen is undergoing reduction and sulfur is undergoing oxidation. So it cannot be disproportionation reaction. Similarly, if you check out the other options also, you will find out the similar pattern. But here if you see in this option, your oxygen is in -1 oxidation state, and the products which is forming here, it has like -2 oxidation state, and here it has 0 oxidation state. So same oxygen is undergoing oxidation over here, and this is going reduction for this particular thing. So same entity here, it is undergoing oxidation. Okay, because the oxidation state is increasing basically. So this is oxidation which is happening right now, and here reduction is happening. So the correct answer for the disproportionation reaction is option number 4. That was pretty simple and pretty straightforward question. Okay, so this was the easiest one. Let's go to the next question then. Let's talk about this particular question. It says that to explain the experimental magnetic moment of the complex at room temperature, the orbital contribution is not required for. Okay, so if you have watched my previous videos on orbital contribution and on the magnetic moment, you might have seen that for the orbital contribution, what you need is that your T2G should be asymmetrically filled. Okay, your T2G or T2 orbital should be asymmetrically filled. In that case only you are going to have orbital contribution. So yeah, the orbital contribution is basically on the T2G asymmetrically filled orbitals. Okay, now you have to just look upon the options here. So in the first one you have cobalt in +2 oxidation state. Now cobalt in +2 oxidation state, and it's a octahedral species, right? So it's a D7 species, and if you look upon this and if you fill the electronic environment of it, so 1 2 3, and it's a low spin complex, sorry, it's a high spin complex. So like 7 you are going to fill them like this. Okay, so this is how I'll be filling 7. Now T2G orbital is obviously asymmetrically filled, so we will have orbital contribution. Okay, orbital contribution will be here. So this cannot be our answer. They are asking that where it is not required. Okay, moving forward for the next one, where it says nickel is in +2 oxidation state, and remember that it's a tetrahedral complex. Now, so it gives you D8 species. Again, you have for the tetrahedral, your T2 orbitals are above and your EG are below. Basically your T2 and E orbitals are there. So if you fill the 8 electrons, so this is how you are going to fill them. So obviously again it is asymmetrically filled, so again you will have a orbital contribution over it. So this is also not going to be the answer. Looking upon option number 3, here you have chromium in +2 oxidation state, and it's a octahedral species, and chromium is actually your D4, right? And again one more thing is over here, that the chromium right now is your low spin complex because of the presence of strong field ligand. So if you fill it, D4 will be filled like this. So 1 2 3 and 4, again you will see that it is asymmetrically filled. So again orbital contribution will be there. In the last one, where you have nickel in +2 oxidation state, octahedral species, D8 complex, and it's going to have octahedral chemical environment. So if you fill the 8 electrons, you will have something like this. Okay, so now you can see that the T2G orbital is symmetrically filled. That means there is no orbital contribution required. So the correct option becomes your option number 4. Okay, so this is pretty simple, directly from my video. So yeah, let's go to the next one then. The next one says that the set of compounds all having polymeric structures. Okay, so for this you should be good at your p block elements, like the chemistry of your p block elements. So there you might have seen that this aluminium and gallium, both of them belong to the same group, and because like both of them belong to the same family. So aluminum fluoride and gallium fluoride, I will attach the structures of them. They all form like they all form polymeric kind of structures, okay. And similarly goes for your tin fluorides, okay, because tin fluoride SnF4 is not a stable structure. It will first dissociate into SnF2 and then it will form like polymers of that. So it will go into that way. So option number 1 is correct option. It was directly from the properties of your p block elements, okay. So nothing to be mentioned over here. One more thing which you can understand, like you can just cancel out option number 3, because obviously this sodium hydride or potassium hydride, they will not form polymeric structures. They have just one electron which is forming the bond with this hydride, and also this MgH2. So these are ionic compounds which will not form the polymeric structures, right? So that's how you can say at this, you can just cancel out this. And again, for your chlorine oxide, bromine oxide, for these also you have seen, although silicon oxide these form polymeric structures, but chlorine oxide does not form it. You have seen the structures of them, okay. So this directly comes from whatever you have studied in the p block elements. Okay, let's go to the next question then. The next one says that the number of electrons transferred for the oxidation of water by the photosystem 2 is, okay. Now this is from your bioinorganic chemistry and it's a direct question basically. So for the photosystem 2, what happens actually, that there is a transfer of 4 electrons in this case. So answer is option number 4, but how it is, let me just explain you a little bit about it. Okay, so this I am telling you from a reference from a research paper, and this is published in Royal Society of Chemistry. It's a very good journal. So yeah, it is said about the photosystem 2 and the oxygen involving, or the oxygen evolving complex. Rest of the theory is given over here. So basically what we have to focus more on is on this particular reaction, where this water is reacting with 2 moles of your PQ and with 4 of your protons, which comes from the stroma, and this is giving us this dioxygen and PQH2, and with 4 hydrogen ion which goes to the lumen, okay. Now this PQ over here is plastoquinone and PQH2 is plastoquinol. So it's all about your like bioinorganic chemistry, and that is directly taken from there. There are few more things which are needed to be focused more, is that because of 4 electrons are transferred, this potential equates to the reaction free energy of this much. So the free energy is quite high for this particular reaction, because there are 4 electrons which will be given in this particular reaction, okay. So the 4 electrons are needed in order to neutralize this particular system. So for the given question it becomes 4 electrons, okay. So it's directly from the topic, so there is not much to be explained, but yeah, if you have studied about photosystem 2, you might know the answer. Let's go to the next question then. Okay, the next one says identify the metal carbonyl which is /R isostructure with OS3CO12 at 298 Kelvin from the following. Now, for that you should know the structure of all of these which are given to you. I'll tell you one shortcut trick, or one way how you can understand these like the carbonyls, metal carbonyl structure. Remember one thing, that if metal is big in size, okay, if metal is big in size and it has metal bonds, okay, if it is so, in that particular case there will be less number of bridging carbonyl, okay, there will be less number of bridging carbonyls. So that is the only thing which is being understood over here in the structure of them. The problem of the bridging carbonyl, there will be more bridging carbonyl in some and there will be less bridging carbonyls in some, okay. So let's talk about this osmium complex OS3CO12. If you calculate, I'm not going to do that, but you can do it of your own. You will find out that there are 3 metal bonds. So you will find out that these osmiums are actually attached to each other through 3 metal bonds, okay. Now if you find out that the 12 carbonyls, they will be attached to them like this, okay. So this is how your 12 carbonyls will be attached. So 4 to each of these osmiums, okay, 4 carbonyls to each osmium. So this is the structure, and they are asking with which of them it is isostructural. So if you look upon it, the first option where it says Fe3CO12, now the iron is comparatively smaller in size. Iron, ruthenium and osmium all lie in the same group, right? So iron is the smallest one in this group. So iron being the smallest one, the metal bond distance will be very small here. okay, compared to osmium bond distance. So for that the structure goes like this. We have again 3 metal bond. If you go with the formula, you will find out 3 metal bonds. So if you calculate that, you will see that one of the iron has 4 carbonyls as the bridging ligands. Okay, it has 4 bridging carbonyls. The rest of the iron only has 3 bridging carbonyls, sorry, 3 terminal carbonyls, and it has rest of the 2 carbonyl as the bridging ones. So one goes like this. Okay, this is one of the bridging carbonyl, and the other one goes like this. Okay, so this is how it is made. Now this is possible, these two bridging carbonyls are possible because of the smaller size of these iron atoms. Now if the size of these iron will increase, obviously the bond length will increase, and then this bridging will not be possible, they will be formed as the terminal one. So for this iron one, if I can tell you, so there are three terminal ones are 10. Okay, there are 10 terminal carbonyls, and the bridging ones are 2. Okay, there are 2 bridging carbonyls. And metal bonds, if I say, so there are 3 metal bonds in all the cases. Now the first option is obviously not isostructural with this, right? Because here you don't have bridging, here you have bridging. So that is not going to be the answer. If you look upon option number B, here again you have 2 iron atoms. So you can replace these two, like these 2 iron atoms will be the same one. One is ruthenium. So you can replace this iron with that ruthenium. So obviously the structure will not get changed that much because you have the same iron metal bond. So the smaller bond, so the carbonyl can be present in the bridging form. So if you look upon the structure, you will find out exactly that in this structure, that is in second one also, where you have Fe2RuCO12, here also you have 2 bridging, and you have 10 terminal ones. Okay, so this is also not going to be the correct answer. Talking about the third one, here you only have 1 iron and 2 ruthenium. So instead of, so this, that iron will be here and 2 ruthenium will be here. Now the metal size has increased. Now as the metal size increases, as I told you that the bridging carbonyl will not exist. So now this particular one will be quite of similar like this. Okay, you will have ruthenium here, and you will have iron over here, and the structure will be isostructural with this. So this is isostructural with this. And talking about the last one, this is again the same because ruthenium is bigger in size and it's quite comparable. Like the size is quite comparable with the osmium. So that's why C and D are your correct options for this particular question. Let's go to the next question then. Okay, so here it says that the first ionization potential of the 3 successive elements in the periodic tables are this, this and this. Okay, so the ionization potential, they are asking that first ionization potential, that for which they will belong. So it's very simple to know. You can just you can just give a order of them. So basically 1086 will be the smallest one, then comes your 1314, and the longest one or the highest ionization enthalpy is 1402. Now if you are talking about carbon, nitrogen and oxygen, nitrogen has a half filled structure, right? Half filled chemical environment or half filled electronic configuration. P orbital is half filled over here. So the like you will be having the highest ionization energy for this, or ionization potential for this. So this particular value, the highest value will correspond to this. Okay, so nitrogen should come in the middle, and rest of them you will know, like you know that the ionization energy increases with decrease in size, right? As the size decreases, it increases. So this particular one, oxygen is smaller in size than carbon. So if you look upon the size, okay, if I just add the size factor, so it goes like carbon is biggest in size, then comes nitrogen, and then comes oxygen. So oxygen is the smallest in size. So ionization enthalpy among carbon and oxygen, if I have to compare, so that is because ionization energy, if I have to compare, so oxygen will have higher ionization energy than carbon. That is because of the size factor. And nitrogen will be highest than all of them because of the electronic configuration, because of half filled electronic configuration. So that's why this particular one belongs to nitrogen, this belongs to oxygen, this belongs to carbon. So here it should be carbon, nitrogen and oxygen, which is there in your option number 2. Talking about the other one, which is boron and other, they are not going to fulfill the same criteria, and the order is not being followed over there basically. Okay, so that's why option number 2 is the correct option. Let's talk about the next question. Here it says that the correct pair of ions for which only ground state J level is populated at the room temperature. Now this particular question is again a direct question from my classes, which I have taken on your lanthanides and actinides. So there we have discussed there is a special kind of lanthanides. These are two exceptional lanthanides where your excited state has more population. Okay, the J level in the ground state. Okay, ground state J level is less, so is less populated. Okay, so less populated, and these two are basically your europium. Okay, these are europium plus 3 and samarium plus 3. So remember, the concept which we have studied is about that the J level in the ground state is less populated, but in the question they have said that the correct pair of ion for which only ground state J level is populated. That means they are asking about the one where it is more populated. Okay, that's what they ask. They are asking basically at the room temperature. So europium and samarium, obviously they are not going to be the answer. Here again samarium comes, so that is not going to be the answer. Here again europium comes, so that's not going to be the answer. The only option where you are not having samarium and europium both, so that is your option number 4. So option 4 is correct, because whatever we have studied, we have to just apply the reverse of that. Many students got confused in it. They have studied in books that the J level, ground state J level is less populated for europium and samarium, and they just thought it, and with that J level, when it came into the exam, they just marked option number 1, but that is not the correct one. Option 4 was the correct question. Okay, let's go to the next one then. The next says that the correct order of stretching frequency of your sulfur oxygen bond, and where M is any metal. Okay, so they are talking about sulfur oxygen bond. So let's take it in this way. So we have 3 compounds basically. You have metal, and with which you have sulfur attached, and with this sulfur you have oxygen attached, and here you have 2 methyl groups attached to this. Okay, you have 2 methyl groups attached to this. This is one of the thing. The other one is you have sulfur, with this you have oxygen, and with that you have 2 methyl already attached. Okay, so that's what it is. Let's make double bond, because sulfur generally forms double bond with oxygen. And the next one is your metal is given to you, and we have oxygen, and then we have sulfur, and with that sulfur you have methyl attached. Okay, so this goes something like this. So fine. And if you look upon option number 2, you have again the same thing, the one which we have done, again the same. The orders are only different here. Okay, so we have to just look upon them. So see how we can solve it, or how we can answer this. So they are talking about the frequency, right? So stretching frequency. What we will understand first of all is about the bond strength. Okay, we'll talk about the bond strength, or basically bond order first of all, because it's simple if you just understand the bond order first, and then you will be able to identify the stretching frequency and the other things. Okay, so let's talk about it. So let's understand it in this way, that in the third one here, if you look upon this, so what is going to happen over here is that oxygen will not favor to form 3 bonds. Okay, it's not going to form 3 bonds. Oxygen generally forms 2 bonds, right? So it's violating the charge, like the valency of this oxygen. So for that, it is going to give it these electron to this sulfur, and this is going to form something like this, MOS. I'm just telling you the basic way how you can approach this question. Okay, the easiest way how you can go through it. So it is having the bond order here, you can say, is about 1. Okay, so bond order is around 1. You can say it's around 1. It's very small. The bond order is very small, or the bond strength is very weak here. Talking about your option number this here, if you look upon this, so what is going to happen, that here methyl is going to apply the inductive effects. These inductive effects are going to increase the the electron density on this sulfur, and if this electron density increases on sulfur, so what sulfur will do, sulfur has the ability that it can take up this electron density, but oxygen being more electronegative, it will fetch out these electrons towards itself. So this is going to happen. Okay, so that's what is going to happen. So which effect is actually happening over here? So obviously inductive effect. Okay, inductive effect of these methyl groups are causing this particular thing to happen, and this sulfur oxygen bond will become a single bond now. Talking about this first one, what is happening over here, you can see that metal generally is in a high oxidation state, or metal is generally electron deficient. Okay, metal generally remains electron deficient. So in that particular case, like these two are applying this inductive effect, the plus I effect, but the metal being electron deficient, it will apply the minus I effect, or it will fetch out the electron density towards itself. So it will not cause that much damage to the sulfur oxygen bond. This is the easiest way how you can go through this particular question. Okay, so that means if I talk about the bond order, okay, the bond order of this, so let me name it as A, name it as B, and name it as C. So for A, your bond order is highest because the sulfur oxygen bond order is highest, because that's not getting disturbed more, right? Because metal is stabilizing whatever electron density is increasing on the sulfur. So that's because of that. So A will have highest bond order. Now talking about B and C, so here inductive effect is there and here the resonance effect is there. So obviously you know that the resonance effect is more like it is more prior, like it is given more priority over the inductive effect. So it means C will make it more weaker. Okay, so bond between oxygen and sulfur will become more weaker over here because of the resonance effect happening on this particular bond. Here the inductive effect is there, so the bond will be weaker, but not as compared to the C1. Okay, so if you have to compare between B and C, so you can say that B has a little stronger bond order than your C. So this is the order of your bond order. So once you got the order of this, you can easily tell that that bond order is actually directly proportional. Okay, bond order is directly proportional to your like frequency, right? To the frequency. So basically the frequency order will also be same. Okay, so stretching frequency order will also be same. So the correct option comes out to be option number 1. So like that you can just understand it. There was not much of concept which you have to understand here, just the basic way how you can approach the question. All right, let's go to the next one then. Over here it says which among the following complexes obey 18 electron rule. Now it's pretty simple how you can do it. The first one here you have Fe2 and CO9. If you calculate it, like if you just calculate the number of electrons, so just look upon it, and you have to calculate the number of bonds. Okay, the number of metal bonds basically. So the total valence electrons will be, from iron you will get 8 electrons each. So it will be 8 into 2 and plus 9 into 2. So basically you are going to get 16 and plus 18. So this is going to give you around like 34, right? So the metal bond is going to be so how many metal bonds you are going to get over here? So 2 metal bonds, right? So because metal bond, if how we calculate that, so 18 into n, that is 2 minus 34, and divided by 2 is going to give you that. So 36 minus 34 by 2 is going to give you 1. So 1 metal bond between. The other one, option number 2, if I talk about this, so we have CrNO4. So we have CrNO4. Now NO can have like it can have two structures, bent or linear both. So based upon the requirement, we can like increase or decrease the number of electrons which will be donated by them. So chromium over here is going to give you 6 electrons, and you are going to get 3 electrons from each of these nitrosyls, which will be linear in shape. Okay, so 3 into 4, so overall you are going to get 18 electrons. So it's again 18 electron species. So A and B both becomes 18 electron species. Talking about the last one, the molybdenum complex over here, if you look upon it, so molybdenum is going to give you, it's in the same family, in the chromium family, chromium, molybdenum and tungsten. So molybdenum is again going to give you, so molybdenum Cn6 4 minus is the one which we have to talk about. So 6 electrons from molybdenum, each of these Cn are going to give you 1 electron each. So you are going to get 6 electrons again, and these 4 electrons from this 4 negative charge. So you are only having 16 electrons, it's not 18 electron species. So this is not following 18 electrons. It's pretty simple, very easy. Option number 3 is correct. A and B are going to be following 18 electron rule. C is not following that. Alright. Let's talk about this particular question over here. It says that the correct order of solubility of silver halides in the liquid ammonia is. Now you might have already studied this particular thing, that the halides basically of all the other metal is soluble in the liquid ammonia, except there are few which are less soluble, which are like your silver, your lead and mercury. These three, like silver, lead and mercury, are the three metals of which, like the halides of whose are little less soluble, or they're not that soluble with the liquid ammonia or with water. Okay, So in this particular question, when you have to decide about the order of them, that which one is actually going to be more soluble in your liquid ammonia, for that you should know about the reaction, what reaction actually happens. So let's say if you have some silver halide and if you treat it with ammonia, so a complex is formed, like this is in solid, in like this solid, this is aqueous, and when the reaction happens, basically a complex is formed. Okay, this is a complex which is formed. Overall the charge remains plus charge and the halogen forms, this is a complex. Okay, this is a complex and it's a soluble complex. Okay, now this particular solubility depends upon many factors like your concentration of the solution and all, but if we keep the concentration constant, and then if I have to tell you that which is more soluble, then over there you have to decide based upon the size of the halides. Okay, because the silver is constant over it, so the size of halide which is actually making this particular complex soluble in the system is going to decide it. Okay, now apart from the size, so if I write down the size order, so the order of the size like goes like this, that my iodine is going to be like the iodide ion, basically it's going to be the highest size, then your bromide, then comes your chloride, and the lowest one is fluoride. So based upon the size factor, you can tell the bigger in the size the halogen, the halide part being bigger in the size, this is going to make this particular complex more stable or more soluble in that particular solution, right? So this soluble complex will be formed more if you have iodine as the halide over there, and it will be least if you have fluoride uh, as the halide over there. So it's pretty simple. You can just look upon this also, that since this silver halide bond is actually breaking, so you can see that if you're talking about silver iodide instead of silver halide, if I have silver iodide and if I treat it with NH3, so it is much easier to form silver ammonia complex. Okay, it is much easier to form this compared to if I have AgF and then if I treat it with ammonia. Okay, so in that case I will have AgNH3 whole twice F. So this particular, like the dissociation of this bond over here is less favored. Okay, is less favored because fluorine being more electronegative, smaller in size, it's going to stick to the halide. Sorry, it's going to stick to the silver very strongly. So that is going to make this formation of this soluble complex less favorable compared to this. So more soluble complex formation, that means making this particular halide more soluble in ammonia. So that's why option number 1 becomes your correct choice. Let's talk about the next question then. Alright, so let's talk about this last question over here, which says that the total number of stereoisomers including enantiomeric pairs for the octahedral complex Ma3BCD is, okay, where A, B, C and D are monodentate ligands. Okay, so whenever this kind of question is asked and whenever you have a single ligand 3 times, always remember that one of the isomer which is very famous, that is facial and meridional isomers will be formed. So first of all, draw facial and meridional of both of them. Okay, so it will be very beneficial if you draw and check. That will be help you to identify the total number of isomers. So let's try to do that. So we'll first of all draw the facial and meridional isomers. Okay, so if I just place all this A on the same face, that is this will be one face, right? A will be one face, and if I place B, C and D, this is going to be called as my facial isomer. Okay, this is facial isomer. Now this facial isomer will be optically active because there is no like mirror plane or anything which can make this particular molecule like symmetrical. So this is optically active. Now if it is optically active, it will have two isomers of that, right? One more enantiomer will be there. So let's say this is R form, so the other one will be S form of that. So two enantiomers will, like two isomers you got till now from the facial one. Now let's draw the meridional one. Okay? So the meridional one will be drawn like this, where you will have the metal at the center, and then you have, now you don't have to put all this A on the same plane. Okay, so I prefer them doing in this way, that is I keep two of them on the axial line and others like this. So B, C and D. Now here this is optically inactive. Okay, this is optically inactive. Why? because you have a plane which is making this particular molecule like symmetrically cutting this molecule like this. Okay, this particular plane which is bisecting this molecule in two half, so that the axial A are going to reflect each other. So this is going to be optically active. I guess you understood, right? This particular plane is the plane which I'm talking about. The plane of symmetry is there. So this is the third isomers which you got. So this is the first one, this is the second one, this is the third one. Now you can just play around with the position of B, C and D, and you can just create the other isomers also. The other one will be like keep A and A as they are. Okay, in the other isomer what you have to do is let this be M and keep your A in the position as they are. So A is here, A is here, A is here. Now what you have to do, just change the element which is, or change the ligand which is trans to A. So earlier it was C, now I'm keeping B here. So C and D I can keep as it is. Okay, so this is going to be my fourth isomer. And the last isomer which I can create will be this, where I have the similar thing, like the position of A is going to be the same. Only what I'm going to do is I'm going to change the ligand which is trans to A. So I have kept C as the trans, I have kept B as the trans. Now the time is for D, so I have kept D as trans. So B and C can be kept like this. So this is going to be my fifth isomer. So total 5 isomers are the one which we will be able to create from this Ma3BCD type of complex. So that's all for this particular video, guys. I hope you guys understood and you guys got to know about all the solutions. And this was the paper from your Assam and Meghalaya region. All the inorganic questions of 2 marker I have taken in this particular video. Thank you so much for watching. If you like this video, give it a like. If you are new to this channel, subscribe to the channel and do share this video with your friends. Thank you so much for watching this video, and I'll see you guys in the next one. Till then, have a great day. Bye bye.